Yeah, a lot of extra credit. Okay. All right, one last stretch, one big old push to the end. Today I want to talk about two different examples about how the lesson I want to teach today kind of is that, and I've said this a million times already, that just looking at the formula for a reaction, just make one up, does not tell you what the kinetics are. Right? The starting materials do not necessarily influence the rate. Rather, the molecules involved in the transition state do. So not all molecules, we talked about this last class, again, you can have two different examples of nucleophilic substitution in organic chemistry, SN1 and SN2. They have the same starting materials, but the kinetics are very different, right? Because the transition states are different, right? Let's just remember that, right? That's a really important thing to know, is that materials don't determine kinetics, mechanisms do. And mechanisms are determined, the kinetics of a mechanism are determined by the transition states, by the intermediates of the reaction, the barriers you have to go over, okay? And so some things, so I'm going to give you two examples today. One is this one that we started last class, this Lindemann-Hinshelwood unimolecular mechanism. And another one's a bimolecular one, where I'm going to teach this lesson that looking at this doesn't tell you the kinetics of a reaction, right? The mechanism. Right? The mechanism can be much more complicated. It can be multiple steps. There could be competition between steps. And so I'm going to look at two different examples of that today. All right, so let's start with this unimolecular reaction, the Lindemann-Hinshelwood mechanism. And again, the idea that we talked about at the end of last class was that in order for a molecule, right, you have A by itself, just one molecule floating in space, has some process to form a new decomposition product. Here's some examples, classic examples, the first ones that come off to my head, things like decomposition. You take vinyl cyanide acrylonitrile and shine a laser at it at 193 nanometers, that's UV light. You form two different there's two different branches, but you form two different sets of products. One is acetylene plus HCN, and the other one is cyanoacetylene plus H2. Okay? So the unimolecular process, you take 1 mole of a molecule, it reacts internally to form 2 new molecules. Another example is an isomerization. This is a classic one, that isomerization between a cyanide and an isocyanide. This has been studied for decades, and actually has very interesting physics. These are unimolecular reactions. Another great example of an isomerization is the rearrangement of acetylene to vanillidine, which is a carbene. There's a lone pair on that external carbon. It kind of looks like ethylene without 2 hydrogens on the end. This is a very important intermediate in combustion. It's very short-lived, very high energy, but the physics of acetylene to vanillidine have been studied for decades and is a very rich chemistry. So these, even though these seem very simple, the chemistry and the kinetics and the mechanisms of them are very rich and very interesting. And a lot of the details about how these work are actually beyond just basic kinetics. You've got to start thinking about quantum mechanics as well. It's a very beautiful story, especially this one, acetylene vanillidine. Hopefully we'll be able to talk about it next semester a bit more. So I want to think about mechanisms of this, right? And the key result that we realize is that in order for A to get over this barrier and form P, you need to have some source of energy, right? It needs to get up to this A star, this activated complex. We'll call this activation, and this is deactivation, right, where you've excited the molecule with enough energy that it can get over the barrier. There's a fast isomerization between A star and P star, and then you have to remove the energy to stabilize P down to the bottom. Right? So this, instead of just going along the line here, we're kind of taking a big jump, crossing over, and then falling down again. Okay. And in order for that to happen, you need something that can provide energy here. Right? Also, you need a place to absorb energy from this as well. That tends to be easier, as we'll see. But we'll focus in particular on this process of A to A star, this activation process. Where do you get this energy from? And what we said at the end of last class is it can't be thermal, right? It can't just absorb radiation from the exterior environment from a reactor. That ends up not being very efficient. And it would imply that the rate of this reaction is dependent on the flux of the heat, how much heat can be transferred from your reactor to your molecules. And the kinetics of this are completely independent of that. Right? The same kinetic rates occur regardless of how efficient your reactor is. Right? It turns out it's dependent on the pressure. Right? And of course, the thing that's really dependent on pressure are collisions. Right? So the Lindemann-Hinshelwood mechanism is to talk about the kinetics of this process, but using collisions to change energy, right? To activate and to deactivate. Okay, and I want to talk a little bit about the mechanism of this today. So let's break it down into steps, right? So the first step is activation. There's going to be a reverse step going backwards. We'll call that -1, right? So you can either go up or go down. There's this fast isomerization between the activated complexes 2, and then there's a relaxation process 3. Okay. So let's think about the kinetics of each elementary step. Okay, so let's look at step 1. That's collisional activation, step 1. And there's 2 ways we can write this. One is we can write that A collides with itself, or another molecule of A, and transfer energy so that one becomes excited and the other one stays the same. Right? Collide. This is an inelastic collision. Okay. Another way is that it could collide with something else, like a molecule of air or the atmosphere, right? Like a helium atom or something, right? Some collision partner M that's not reactive, and you get this, right? It could be itself or it could be another molecule. Often we do these experiments in imagine we have a solvent. These are our solutes, these molecules, and we do it in a solvent, a gas solvent, if you will, like helium. Helium acts as our bath, our collision partner. Right, so M would be helium in this case. Typically, all right. Typically, right, some non-reactive material, nitrogen, argon, helium, stuff like that. Okay, and then the next step is you've gotten up to this barrier, and now you're in equilibrium between the products, the reactants, and the products, right? A and P star. Right, so this is a fast isomerization to P star. Right, notice that the Gibbs energy difference between A star and P star in this case is 0. So they're at equilibrium with each other. Like this, or P star. And this is usually very, very fast. This is on the order of a molecular vibration, which implies a rate constant of about 10 to the 15 per second. All right, so if you think about, like, if you go back to organic chemistry, you think about CH stretches, which are at 3,000 wave numbers. You know, CH stretch here or something like that. You know, a vibrational frequency. Those are about 3,000 wave numbers. If you convert that to time, you get about a femtosecond, which is 10 to the minus 15. So the rate constant is 1 over that. It's about 10 to the 15. It's pretty fast. Could be faster, could be slower. It depends on the process. In fact, in vanillidine, this isomerization, depending on what A star state you're in, that can be really, really slow. It can be on the order of 10 to the minus 6, 10 to the 6. Right? So there are different cases, but we're just going to assume that it's very fast. Right? That's a fair assumption. There are exceptions, but for most part, that's a reasonable thing to do. And then the last step is collisional deactivation. or just deactivation, or it could be any other process, which is P star to P. Okay? It could be a collision that causes this. It would maybe look something like this. Sorry, so P star was P, goes to P plus P, right? Something like that. Or P star can emit light, a photon, and remove its energy through light. Right? This is called, we'll talk about the rates in a second. Okay, so we have a couple different processes here. I'm going to label the rates for each one. This one's K1. This one's K minus 1. It's the reverse. We'll call this K2. And we'll call this K3. Okay. And we'll also say this is some other constant. This is actually what's called, the rate for this is called the Einstein rate. So I'm going to call this K Einstein. Right? Every molecule has a probability to emit a photon if it's excited. And it's determined by what's called the Einstein rate. We don't have the theory to talk about the Einstein rate, but it's non-zero, and there's a probability that it can just lose its energy by emitting light. Okay. And in fact, most molecules do it that way. Okay, so let's think about the kinetics of each of these steps. Write the rate laws for each. So I'll put them over here. So I'll write the rate laws for each step. And I want to write we have to decide what material we want to track the concentration of, right? Because the rate law is going to be the concentration with respect to time of some material. And I want to focus in on A star, right? Because this seems to be the thing that really determines everything, right? A can't become P until it becomes A star, and vice versa. So A star kind of seems to be the focus of our reaction. So I'm going to write everything in terms of A star. So step 1 is dA star dt is equal to K1. And let's think about what it's equal to. Well, in order to make A star, you have to collide two equivalents of A together. Or A times M, whatever you want to write. Right, so we'll just assume that M is A here, just to make the math easier. So the rate to form A star is second order. It requires two equivalents of A. All right, and then 2. All right, let's do minus 1. All right, minus 1 is the backwards. Of course, all we have to write here is equal to minus K minus 1. And that's going to be A star A. All right, the reverse rate, oh, sorry, this is A star plus A goes to A plus A. That's K minus 1, I apologize. Right, so you need to have A, your excited A, and you need to collide it with another collision partner that has less energy and then transfer the energy away. Right, so you still need two bodies for deactivation as well. Step 2 is just really easy. It's just a first order reaction. It's going to be K2 times A star. And then the final rate is equal to minus K3 A star. Well, it's actually minus 3 A3 P star. Okay, but we can write this as minus K3 A star because K2 is fast. Okay. So we have all the equations written down. Now what we can do is combine them and ask what the total rate of A star is. So let me write this here. Total rate, where the hell can I put this? Oh, let's put it over here. Don't need these examples anymore. So the total rate is going to be dA star dt. So let's go across all the, it can be produced with K by K1. It can be depleted by K minus 1, the reverse reaction. And it can be gotten rid of by K3 It's actually K3, K2, K3 times A star. Okay, so we can create it by colliding A's, we can remove it by deactivating it, and we can react it by forming P. Or get rid of it by forming P, which is this last step. So this is forming P. This is A star to A. This is A to A star. All right, so it's the sum of all these rates. Now I'm going to make an approximation. All right, because we can't really do anything with this. Right? We can write it down, but in order to understand how A star's concentration changes, we need to know A and A star. Right? So we have a couple of variables. Maybe we can get rid of one of them. So what I'm going to assume, I'll write this in a different color to accentuate its importance. The assumption is that A star, the concentration of A star is constant. It is destroyed just as fast as it's formed. Right? And this seems to be a reasonable approximation. Because once A star is formed, either it's going to immediately come over here at a very fast rate, or it's going to just be destroyed and go back to A. Right? So A star is temporary. It's a metastable region. It only exists for a short amount of time. And that means that its concentration is constant. Right? Every time you make one, it's either just going to go immediately over here, or it's going to come back down. It's got no other options. You can't just stay here. Right? So A star is constant. Therefore, its derivative is equal to 0. Right? Right? Concentration is unchanging in time, so its derivative with respect to time is 0. So we have a name for this, and it's used all the time in kinetics. It's called the steady state approximation. Right? We can simplify our kinetics by assuming some of the intermediates are short-lived on the scale of the time scale of the reaction, and we can neglect them. Right? This is saying some intermediates don't exist for any appreciable amount of time. Right? It's like when you fly from New York to California, you might stop in Iowa, but the concentration of people in Iowa is not constant because it's a flyover state, so they come in and they immediately get the hell out of there, right? It's the same idea. It's an intermediate. Sorry for anybody who's from Iowa. Right, but it's the same idea, right? You have to, in order to get from A to P, you have to go through A star, but you're not going to stay there very long, right? So the concentration of A star is constant. All right? And so that makes it nice because this is all equal to 0. Okay, so we can solve for the concentration of A star, and that'll give us a function of A. Right? So the concentration of A star will be dependent on how much A we have initially. All right, so let's do that math real quick. Well, I'll just rewrite the equation on the board. So we have 0 equals K1 A squared minus K minus 1 A star A minus K2 K3. I'm going to rename this to, I'm just going to call this K2. All right, just I don't have to keep writing it. A star. All right, I'm going to call it big K2. Like that. Okay, and we can solve for A star. Right? Since the concentration is constant, it seems reasonable to solve for it. Okay, when you do that, you find, I'm not going to do the algebra, but the algebra is not too hard. A star is equal to K1 A squared divided by K minus 1 plus K2A. Is that right? Do I have this right? Oh, no, sorry, I have it wrong. Sorry, it's K2 plus K minus 1A. Okay, and so if we plug this into our formula for the creation of P, just remember that dP dt is equal to K2, the rate of creation of P, times the concentration of P, or sorry, the concentration of A star, right? That's what this is. Concentration of A star. So that means that the rate of product formation is going to be equal to K2 times this number, K1 A squared, right? We just plug in the concentration of A star into our expression. So now we can express the formation of our products with respect to our reactants. Right? And let's look at this equation for a second. And what we can notice is that this is not first order, right? It's approximately second order. Right? So the rate, just from first approximation, says that the rate kind of looks like A squared. Right? So this is approximately second order. What this says is that in order to do unimolecular reaction, the rate is second order, which requires two equivalents of A. Right? So again, a single molecular reaction, a unimolecular reaction, is in fact a bimolecular reaction because you need an extra body for the energy transfer, the collision. Right? That's the activation, if you will, the activator. Right? So it's approximately second order. All right, but we can look at the limiting cases of this expression and see if we come up with something that seems more reasonable. So let's assume we have two limits. One is that assume collisions occur faster than the formation of P, or K2. Right? So let's assume that the system's always colliding with itself. Okay? So the process of this K2 reaction, the thing of taking A star to P, is slow relative to the collisional activation and deactivation of A. Right? So there's lots of collisions. Right? So this is high pressure, right? Which means lots of collisions. All right, so what this means is that K1, sorry, just a sec, K minus 1, sorry, right, the collisional deactivation of A is much faster than K2 times A star, which is the formation of P. All right, so this is collisions to bring A star back down to A. That's faster than this process. All right, so it's more likely that it's going to go backwards than forwards. So we notice that we can cancel out the A stars here. They don't matter. So we're left with K minus 1A is much greater than K2. Okay. Now look, but notice we have both of those terms in our denominator here. Okay, so dP dt is equal to K1, K2, A squared. I'll just rewrite it. K2 plus K minus 1, A. And this term is really big, and this term is really small, comparatively. So we can neglect it. And what we're left with is K1 times K2 over K minus 1. And notice the factor of A cancels out. You have A star, you have A here and A squared. So you're left with just A, first order. So at high pressure, or fast collisions, unimolecular reactions are first order. Exactly what we would expect. Right, the idea is that the system's always colliding, so the collisions don't matter. They're not the rate limiting step anymore, because they're always happening. So the rate limiting step is just the conversion of A to P. So therefore, you get first order kinetics. Right? So the system looks more like what we would expect, that the molecule magically converts to P, and its kinetics are proportional to that. However, what if we assume the opposite? What if, assume low pressure, which means that K2 is much faster than K minus 1A. Right? So the collisions are really slow, and the reaction relatively is fast. Then if we write our expression for dP dt, we're left with K1, K2 alpha squared, or A squared, K2 plus K minus 1, A. If K2 is big, and this is small, right, so we can neglect this term, and we're left with K1 alpha squared. So now the rate is second order and dependent on the collision rate, right, K1. Okay. So what the point of this is that in the gas phase, all reactions that are in appreciably low pressure, right? If you basically effectively have a molecule kind of on its own, you absolutely need a second body for it to react, A squared, right? Second order, right? You have to wait for that collision to occur before anything happens. So you got to have a two-body process. But if you're colliding constantly, if you're at high pressure or say for instance in solution, right? In liquid phase, you're always colliding with the solution, right? The solution, the solvent, is always providing a sink of energy, right? It can absorb energy through collisions, it can absorb energy through vibrational energy transfer. There's all sorts of different ways a solvent can absorb energy from a reaction. So you're at high pressure limit, and so it's first order, exactly what you would expect. Okay? And this is really, really important in the gas phase because this tells you why the interstellar medium, for instance, just space itself, where chemistry first forms, is very sparse in terms of complex chemistry, right? You know, something like 200 molecules in space, and they're all kind of the same style molecules. We don't see a lot of the complexity we see on Earth because the system's at low pressure, right? For a long time, scientists thought that there's no possible way you could create molecules in space because they understood this mechanism, right? They said, in order for a molecule to form a new molecule, you need to have another body collide with it. But when the average density of space is 1 hydrogen atom per milliliter, it takes a really long time to find a collision partner. So there's no possible way to build chemical complexity in space because the rates are dependent on collisions and there aren't any collisions. Right? It might take hundreds of years for a molecule to find something to collide with. Okay, what they didn't realize is that there are surfaces and interesting phases in space, and grains and dust, things that molecules can absorb on, and then chemistry can happen. But they understood this idea of gas-phase kinetics. Even worse in the low barrier, and I'll show you an example of this in just a sec. In the low pressure case, if this were a bimolecular reaction, you're taking 2 molecules to make a new one, you need a third body on top of that. It's third order. You need your 2 bodies to come together and a collision partner to stabilize it. So in order to do a bimolecular reaction, you need 3 bodies, and that's going to be anywhere from 1,000 to 1,000,000 times less likely than a 2-body collision, depending on the pressure and the speed. So the idea is that's why, for instance, things aren't that reactive. Or you don't do organic chemistry in the gas phase because the kinetics just aren't amenable for reactivity, right? However, we tend to use gas phase for things when we need other energy sources, like using lasers to drive chemistry. Gas phase is really good for that. But for typical collision-based chemistry, normal chemistry, if you will, normal reactions, the gas phase is just not that efficient because there aren't that many collisions. Okay. All right, so I'm going to show an example of this from actual literature. And then whatever time we have left, I have one more mechanism I want to talk about.
Before you go on,
Yeah.
can I ask a question?
Sure.
Can you explain again why you crossed out the K minus 1 on the denominator?
Oh, I'm just assuming that relative to K2, this is a small number. So if you add K2 plus a small number, it's approximately K2.
Okay, thank
So I'm just making it 0. Right? It's a really common way to approximate. Just If you got a really big, if this is 10 to the 12 and this is 10 to the 4, then adding 10 to the 4, 10 to 12 is not going to change anything. So that's a small change, so we can just neglect it. Okay, right, so here's an example. This is a bimolecular example, but it's a reasonable one. What we're going to do is we're going to take nitrous oxide, NO, and we're going to react it with oxygen, triplet oxygen. That's not so important. There's two different oxygen isomers, singlet and triplet, but triplet's the common one. And react it to form NO2, all in the gas phase. Okay. All right, so this is a radical-radical combination. Right? We're adding two radicals together. Radicals like to come together. They have no barrier. It's a barrierless process. And it's also exothermic. Delta H is minus 300 kilojoules per mole. Right? So it's a really downhill and there's no barrier. So if we were going to draw a reaction coordinate for this system, here's our NO plus O, and it just goes straight down to NO2. It loses 300 kilojoules per mole. All right, well, this is the best reaction ever. It doesn't need to gain energy, and it's downhill. So it's favored by equilibrium, and it's fast, or so we think. But let's think about what happens. Let's use this idea of Lindemann-Hinshelwood to think about what we have to do in order to make NO2. So you have NO and O come together, right? There's no barrier. So as they come together, they're going to stick together, but they're not going to lose any energy.
So that's three radicals you have?
No, sorry. No. This is triplet. Sorry, I'll just get rid of that.
Okay.
Yeah, it's this. There's oxygen has oxygen can be in two spin forms, singlet or triplet. I should just ignore that. So if you make oxygen atoms, most of the time they're triplet, so it doesn't matter.
I get what you're saying.
Yeah, no worries. So when they combine, they don't lose any energy, right? Energy conservation. They just come together. There's no barrier. And so when they immediately combine, what energy are they at? Well, they're right here. Right? They're well above the ground state, if you will. Right? So what you actually form is an excited NO2 molecule. Right? And that excited NO2 molecule is in equilibrium with the radicals, right? The same energy, K is 1 in this case. Right? So in order for this reaction to stabilize NO2, you need to have some process to bring it back down. Right? So here you need a collision. It turns out that NO2 isn't very efficient at emitting a photon. The Einstein rate for NO2 is pretty slow. So at low pressure, you need to collide with it. Okay? So even though everything screams that this is an efficient reaction, no barrier, exothermic, delta G is less than 0, it should just go at any temperature. But in fact, it has a very, very distinct pressure dependence, because in order to actually form NO2, you have to collide with something. You have to have a collision. So let me draw the experimental results. If we plot the concentration of NO in millimolar on the x-axis, let me make this a little bigger so it's easier to see. So we're going to plot the concentration of NO in units of millimolar on this axis, and on this axis, the y-axis, we're going to plot the rate. And I'm going to multiply it by 10 to the 4. Okay, so you'll see why in a second. It gives me nice numbers. All right, and my plot is going to be between 0 millimolar and 2 millimolar. I pulled this data straight out of the paper. And K-obs is between 2 and 0 times 10 to the minus 10 to the 4. 10 to the minus 4. All right, so just as a reminder, this means that these numbers are multiplied by 10 to the are bigger by 10 to the 4, so this is actually 1 times 10 to the minus 4 on the scale. It doesn't really matter in this case. I really just care about the curvature of this curve. And if we predict what this curve would look like, the rate constant versus NO, if we assume unimolecular first order theory, we would predict from Lindemann-Hinshelwood, let me see where this curve is, ends at 2, 2. So Lindemann-Hinshelwood predicts a straight line like this. So they activate the A, if you will, at 0 concentration. The Arrhenius prefactor is on the order of 10 to the minus 4, 1 times 10 to the minus 4, and then it increases linearly with concentration. Okay? So that's Lindemann-Hinshelwood high pressure. All right, that's what we would expect if this is a normal reaction. But what you see, I'm going to draw a vertical line here. What you see is experimentally, I'm going to draw the experiment in a different color that isn't being used yet, so we'll do it in green. Is at a high pressure, this experiment, so experiment is green. At high pressure it agrees nicely, but as you start to cool off, or as you start to reduce the pressure, where does this cut off at? 0.5. The system starts to deviate like this. So this is experiment. Okay, and so if you model this, this is proportional to NO, linear, first order. And at low pressure, this is all at the same, this is all at 298 Kelvin, just FYI, this is a T equals 298. This is proportional to NO squared, second order. Okay, so you can clearly see in the system the effect of how collision stabilizes the system, that you need an extra body. In the presence of many extra bodies to collide with, right, which is high pressure, every time you make an NO2, an activated NO2, it's going to find something to collide with and it'll cool, okay, to NO2. Right? So you get linear relationship. Right? Every NO2 star you make, it's going to find a collision body to cool with, to transfer energy with. But there's going to be a low pressure regime at some point where the rate of going backwards is faster than the rate to cool to the minimum at low pressure. Right? In that case, we get to the low pressure limit, which is second order. And so you have this quadratic dependence on the rate and concentration. Right? So you can do this for all sorts of gas phase reactions, and of course, depending on how the energetics of the gas phase reaction, where this high and low pressure cutoff occurs. But in general, you're going to find this, that gas phase reactions are second order at low pressure, and they're first order at high pressure. And then you can keep extrapolating this all the way up to liquid phase, solution phase, and you'll keep seeing first order. But there's this really interesting region in the gas phase that you can only see in the gas phase at low pressure where collisions dominate, or sorry, the effective collisions dominate and are what ultimately determine your rate, right? So even if you have a fast, efficient reaction, if you can't stabilize the energy, you're never going to be able to do it fast, right? It's not efficient, right? So that's a really interesting, I think that's a really interesting story because it's somewhat counterintuitive. If you give this to an organic chemistry student and ask them, is this an efficient reaction? Well, yeah, delta H is less than 0 and there's no barrier. The kinetics are fast. But you have to get rid of that energy somehow because the system's just going to equilibrate backwards if you can't get rid of it. Okay. Any questions about that? Okay. Almost thought I had a question there. No? All right. Yeah, so there are exceptions to this rule. Some reactions are just inherently slow. This process is slow, so you get first order no matter what. And unfortunately, we just don't have the language to talk about those yet. But there are really, really special cases and really interesting chemistry about systems that have very, very slow isomerization between the activated complex and the starting materials. And so that they're first order even at low pressure. Because once you get it over here, it really can't go back very effectively, or it oscillates between the two. That can also happen. This just oscillates back and forth, and so eventually your stuff just moves back to NO2. Eventually it just kind of trickles down the energy well. And so your kinetics end up being roughly first order, even though you're at low pressure, because this reversibility is not that efficient. Right? So there are definitely cases of that, and that's typically due to quantum mechanics. Quantum mechanical effects, which we're not talking about here, usually cause those things.
I know there's no order in between the two, but did they test that medium pressure and see if there was, or there's just no reaction that occurs?
What do you mean by medium pressure?
Well, you said low pressure and high pressure.
Well, yeah, I just mean that in the sense, yeah, I would call the intermediate is right in the middle. What I mean by low and high is where the that's a relative sense, in the sense of where do the collisions dominate the rate and where they don't. So that number, the scale, the concentration depends on the reaction itself. It's not like a hard cutoff. This is actually, in my view, this is a lot of pressure in general. 1 millimole of NO at one, geez, I got to think about that for a second. Well, that's like 10 millibar of pressure. That's a pretty significant amount of pressure for gas phase. It's about a torr, a torr to 10 torr. That's a lot of pressure. So I'd call all of these high pressure. Interestingly, if this wasn't so exothermic, if for instance it went like this instead, there's much less excess energy to remove, and the reaction will be first order at a much lower pressure, right? Because there's less energy to remove. It's more likely to get rid of a small amount of energy than it is a large amount of energy. So in some ways, the fact that it's so exothermic is a bad thing. It makes it worse because you have more energy to get rid of. So it almost would be better for it to be less exothermic, and the kinetics would be more efficient at a fixed concentration. Yeah, so the energy difference is important.
I feel like chemistry is just learning something and then learning
Yeah,
later.
that's right. What's that book called? All the things my teacher lied with.
Exactly.
Yeah, that's
It's
what
just a
chemistry is.
cycle.
Yeah, no, that's exactly right.
It's
Yeah,
like remember
I like to say everything you learn in general chemistry is wrong.
No, but even just now, like we were like, oh well, this is going to be the answer because of this, and it's like, nah, you're wrong.
Yeah, it's interesting, right? Everything is about. The thing about chemistry is an approximative science, right? Chemistry is very complex, but we can if we make some very simple assumptions, we can come up with really simple ideas. But there are always exceptions. Next semester, we're going to learn, like when you learn about Vesper theory and valence bond theory, you learn about structures. That Vesper theory and valence bond theory are total and utter archaic garbage. I don't know why they still teach them anymore, because you can write down a million different exceptions to these things.
Should we just forget everything from Gen Chem?
Yeah, they should teach this first. Unfortunately, you got to do the math, which is the problem.
Learn stuff in Gen Chem?
All right, so I want to do one last example, which we have just enough time for, and I want to just do another lesson of don't look at the reaction formula and think the kinetics are explained by the reaction. And the reaction I want to talk about is a really simple one. It's H2 plus Br2. Oh, sorry. Let me see if I can write in the gas phase to make 2 HBr. Really simple reaction, right? Classic bimolecular substitution, right? Just swapping atoms. The rate of this reaction is not right? If you look at that formula, you would say, okay, the rate's probably this, right? 1 mole of H2, 1 mole of Br2. It's not. In fact, I'll write the rate down, I'll spoil it for you. And we'll explain why. The real rate is much more complicated. There's one rate called the forward rate that's proportional to BR2 to the 3/2 power times H2 divided by concentration of BR2 plus a reverse rate HBr. Very different, right? It's very strange, right? We would not predict this, right? Not only is the formation HBr dependent on its reactants, but it's in weird powers, but it's also anti-dependent on its own concentration, right? HBr's formation is suppressed by the presence of HBr. Right? There's some feedback loop in this system, right? So the reason why this is because this is not a single step mechanism. Multiple steps occur. There are multiple high barrier intermediate steps. Right, and I kind of want to walk through this derivation just to give it a sense of the complexity of kinetics. And what I'm going to do is I'm going to spoil the mechanism first, and then what we'll do is we'll derive the rates from the mechanism. So the first step is breaking bromine into 2 bromine atoms. We'll call this K1. All right, so this has a rate equal to K1, rate constant K1. All right, so this is what we call an initiation reaction. This is a free radical reaction. That's what we call initiation. This is slow, right? Because we have to break a bond. Right, we have to break the Br2 bond to form 2 atoms, 2 radicals. So that's not only endothermic, but there's also a barrier associated with it, so it's slow. All right, so we have a slow step at the beginning. And then we can do chemistry with that new bromine radical, that bromine atom we create, by having it react with H2 to form HBr and a hydrogen atom. All right, we'll give this rate K2. And this is what's called propagation, right? We're moving that free radical from one species to another. And we get rid of the free electron on the bromine and put it on the hydrogen. This can then go back and react with Br2 to form HBr and H. Wait a second. Oh, that doesn't make any sense. HBr and Br, sorry. Wait, what's going on? Yeah. Sorry. Right? So we can have both processes. We can have the H transfer to bromine. We can have the bromine transfer its electron to hydrogen. Right? We can have both steps. Call this K3. This is also a propagation step, right? We're just moving the unpaired electron around. And then the 4th step is termination, which is where we get rid of the which is H plus HBr goes to Br2 plus H. Is that right? Do I have that right? No, sorry. I'm reading this wrong. Sorry, H2 plus Br. My apologies. I got that right. This is so this is K4, termination. And 5. The final step is the final termination step where 2 bromines can, basically the reverse of the first step, 2 bromines can combine to make Br2. All right, we'll call this K5. All right, so this is the mechanism of the reaction, right? The fact of the matter is that you can have this radical either on the hydrogen or on the bromine, so you have to consider the fact that they can react with all each other, right? That they can all move around. Right? So you have basically a chain reaction here, right? We create a radical which then propagates, that continues to propagate and makes Br again, so that can happen again, right? This reaction creates H plus, or H radical, H atom, which then can form Br again, which then can react to form H plus, right? So you have this chain reaction occurring. It can also propagate a different way to make H2, and then the reaction go backwards and end, right? So there's this like feedback loop of reactions that are occurring, and that's what causes this to become very complicated, because you have this feedback loop occurring, right? It's not just a forward reaction, but you have multiple competing reactions going backwards and forwards and sideways. Right? And that's going to complicate the mechanics, because some of these have barriers and they're appreciable, right? And so you're going to have to deal with multiple barriers. So what I'm going to do, though, is I'm going to do the steady state approximation. So I'm going to apply steady state to the materials that I think aren't going to stick around very much. So there's two really good places for that. So what we'll do is we'll apply it to Br radical, right? Every time, right, radicals like to combine with stuff. They don't like to exist for very long. So we'll assume that that doesn't last for very long. And for H. Right? Basically, every time these get created, they get destroyed. Seems like a reasonable approximation to make. Right, so we know that we are doing a steady state approximation for these. We can calculate the rate of formation for these and set them equal to 0. Right, so we have two equations. And I'll write this one lower, because we'll have to write them out. Okay, and so let's go through this mechanism and think about where bromine's getting created and where it's getting destroyed. So for instance, it's getting created by K1 times the concentration of Br2. We need to multiply, but we have to multiply this by 2 because you create 2 mole equivalents for 1. So you have to double it to 2 just to keep the stoichiometric ratio correct. It gets destroyed by step 2. Right? So that's going to be destroyed by K2, and that's going to be times the concentration of bromine atom times H2. It gets created by step 3, right? That's the converting an H atom to a Br radical, or propagating the free electron. That's going to be K3 times H times Br2. It also gets created by step 4, right? This termination process makes Br. So that's going to be KRH, K4H times HBr. And then 2 converting into 1 at the end. So this is a minus sign. We have a factor of 2 because of the 2-to-1 difference in stoichiometric ratio. And it's proportional to the concentration of bromine atom squared. Okay? So all I've done is I've assumed that each of these steps are elementary steps and that their transition states involve both all the molecules in it. All right? And just set them and then added all the rates together, the ones that create and ones that destroy. Okay? So we can do that for both species. H2 is a little easier. This is going to be, H is a little easier. It's K2, Br, H2, minus K3, H, Br2, minus K4, H, HBr. Okay? All right, so just as a reminder, let's just go through this. Looking for the hydrogen atom. It gets created by K2, right? The propagation step. So it's positive. It gets destroyed by the second propagation step, step 3. Right? H atom goes to a Br atom. So that's a minus sign. And it also gets destroyed by the termination step. The first termination step, step 4. Okay? And it's not involved in 5. Okay? So we have 2 equations set equal to 0 and 2 unknowns, so we can solve simultaneously. Just like before, H bar, the concentration of H bar is a constant, and Br. Okay, so it's just a little bit of algebra. It looks ugly, but it's really not too bad. You can solve for H here pretty easily, then plug it into here and solve for Br. No, math is not too difficult. It's just a little involved. And let me make sure I get my equation right. And what you find is that the steady state concentration of bromine atom is the square root of K1 over K5 times the square root of the bromine concentration. Isn't that interesting? Right? That's because we have all these competing reactions. You end up getting weird kinetics because you have some things that are accelerating the reaction and some things that are decelerating the reaction. And so you end up getting steady state concentrations that look a little funky. And H is even weirder. It's K2 times the square root of K1 over K5. Oh, and it's got a nasty Br2 to the 1/2 H2 divided by K3 Br2 plus K4 HBr. Okay, so the production of hydrogen atom is promoted by the presence of H2 and Br2. Well, that makes a lot of sense because in order to get H atom, you have to create Br atom from Br2 and then react with H2. All right, so if you combine these two reactions, the concentration of H atom is dependent on the presence of Br2 and H2, right? Because they're the things that really contribute to this reaction. Right? The Brs kind of go away, if you will. Right? They kind of cancel out. Meanwhile, the reaction is deaccelerated by the presence of bromine and HBr. And that's not that surprising because in those two reactions, you lose H by the presence of HBr and Br2, right? So you get a destructive element here and a creation element of H. This creates H and these destroy H. So the creation's on the numerator and the rate is slowed by the things in the denominator, which are the things that destroy it, right? So this is, you can think of this as the creation rate divided by the destruction rate. And that makes sense. If you think about the rates, the ratio of the rates, you get like an equilibrium constant, which is proportional to the concentration, right? The more creation, the faster you can create, the more H you're going to make. The slower the creation is, the less you're going to have because it gets destroyed by the destruction mechanism. Okay, so we have all this complicated stuff, right? But we have these really nice expressions now for our steady state concentration, so we don't ever have to think about bromine atom and hydrogen atom anymore. We could just express them with respect to our starting materials and our products, right? There's an equal competition. And so when you plug this all in, let me get the right formula here. So what we're interested in is the formation of products. So let's look at that. Let's first calculate dHBr dt. Where does HBr get created? Well, it gets created by K2. It gets created by K3. And it gets destroyed by K4. Okay? Again, our expression for the creation of HBr has hydrogen and bromine atoms in it, but we can substitute those because we applied steady state and we got nice expressions for them, right? So we can plug these in, right? We can get rid of the H and the Br because we can't measure the concentrations of these because they get destroyed, right? So, but they're created proportional to these numbers. They're still there. We just don't exist at that point for very much. So sub in steady state H and Br. Okay, and there's a bunch of math you got to do. So just to simplify, let's let the total reaction rate, the pseudo rate as we call it, K sub R, be 2K2 times K1 over K5. And the reverse rate, Kr prime, as K4 over K3. I'm just making simplifications so the math looks nicer. And that should make sense. K4 and K3. Yeah, we're just putting them all together, sorry. And what we get, I'm just going to erase this. I'm just going to do the math. I'm just going to do the math for you. And what you end up getting is Kr Br2 times the 3/2 times H2 over Br2 plus Kr prime HBr. Okay? So what this is this right here is what we call the forward rate. Right? This is our creation rate. And this is our destruction rate, right? The go backwards. Right? Your radicals can react with HBr and bring you back to Br2 and H2, but we also have a competition for the forward rate where you combine Br2 and H2 to make HBr. Right? So you have a balance between the two. Okay? Right? And so you can get these really, really complicated expressions because you have multiple react steps, competing steps, right? You have a couple slow steps, you have some fast steps, and the combination of that leads to very complicated kinetics that don't necessarily, at least immediately, seem obvious where they come from. Right? So if we were to do the kinetics of this, right? If we were to measure it, the typical way, which is to change the concentrations of Br2 and H2 and watch the rate, we would notice that you would get an order of 3/2 here. But notice in fact, so let's do this. So start with no HBr in your system, right? And high Br2 concentration, all right? So you flood the system with bromine. So if you flood the system with bromine, what happens? Well, this term is much bigger than this one. So you have, let's do the numerator. That doesn't change. But in the denominator, this term right here is much bigger than this one. So you're left with Br2. Right? And so this ends up being Kr Br2 to the 1/2 times H2. Right? These kind of look second order. Not exactly. Right? It's 1/2 instead of a 2. Instead of the squared. Or sorry, 3/2 minus 1, yeah, 1/2, right? So it's not quite second order, but it's almost second order, right? And so we would expect that if X has Br2, this system's just going to go to completion as much as it can, so it ends up looking a lot like what you would expect, right? You have a molecule of H2, a molecule of Br2 to make HBr. You would expect somewhat second order mechanics. They're not perfect, but they're close, right? Because the competition still plays a role. Likewise, if you do it in the excess and where you have minimal Br2, you're left with Kr Br2 3/2 times H2. This term's big, this term's small. So we're left with Kr prime HBr. Right? And this kind of looks like Kr Br2 times an equilibrium constant. Right? So when you're at minimal Br2, you have an equilibrium between HBr and H2 Br2. So they go back and forth. And depending on the temperature, it might be product favored or reactant favored, but ultimately the rate's going to be determined on the equilibrium between BR2 and HBr times BR2. Right? So the kinetics are still weird, but this KEQ looks like BR2 H2 over HBr. Actually, this is 1 over KEQ. So this is equal to the reaction rate times the bromine concentration divided by the equilibrium constant of the reaction. Right, so the idea is that, so if this is large, right, if you have a lot of HBr in your system, the rate of HBr slows down, right, because you have so much HBr in there that it wants to back react. So your rate of formation of HBr decreases because there's already too much HBr in the system, and it's going to want to react to go back to H2 and Br2. Meanwhile, if your system's in a situation where you have no HBr and a lot of starting products, then KEQ is going to be is going to be a small number, and so the rate's going to be large. Okay, so here this is a case of competition. This is honest to God competition where you have this process is competitive with this process kinetically. They can go back and forth, and so your ultimate rate depends on the concentrations of your reactants and products, Le Chatillier's principle. And the more products you get in your system, the more likely the rate's going to switch back to wanting to go backwards. And the less products you have, the more likely it's going to want to go forwards to form products. Because the thing is damped by the equilibrium constant. Right? So the denominator is proportional to the concentration of the products, which means it'll slow down the more you have. So when you want to make HBr from H2 and Br2, what you have to do is use Le Chatillier's principle. Because if you just leave them all in one system, they're going to equilibrate and move back and forth, and you're not going to make a lot of HBr. You're not going to have complete conversion. So what you have to do is react H2 and Br2 and then condense the HBr out, which will drive the reaction towards HBr. Okay, so this reaction is in a constant equilibrium. There's competition between the two. And so in order to speed the reaction up, you need to liquefy the products, pull them out of the equilibrium so that the system can be driven forward. And this often happens with chain reactions. They generate a lot of energy, they occur quickly, but they can also occur quickly backwards. And so in order to drive it forward, you need to make sure that you pull your products out. Okay, so if you just, you might only get 50% completion if you leave everything to equilibrate by itself. But if you can condense your HBr and pull it out, then you can get complete conversion because the rate's going to be pushed towards the products. Okay. I know that was a lot. I wanted to give this as an example of kind of the complications of kinetics. You won't have to derive a giant rate law like this on the exam. That's not really what I'm interested in. I just wanted to give you a case of why these things can become complicated. You can spend a whole year thinking about this stuff. It's a real, graduate level courses, you're going to learn this stuff. But I thought I'd give you an introduction to it. Okay, we're done. Thanks, everybody. I'll see most of you in like I'll see you in 2 weeks, but what?
My beautiful end of physical chemistry one.
All right, okay. Make sure to relax.
What time for that?
I'll try to.
Yeah.
There's no graduate seminar.